taking a look at electron dot diagrams of elements on ions. Oftentimes, I would call this an elements Lewis dot diagram. I use those words interchangeably. However, we do know what this looks like. When we draw an electron dot diagram, we're not drawing all of the orbitals. What we are going to draw is valence electrons. So, really important to be able to count these. I've just taken two examples from our notes or our practice, number 5. So we're going to do sodium and argon. Sodium is in group 1. So if we're counting across, we are going to count group 1. And we see that it just has one valence electron, again, because it is in group 1. So one valence electron. Therefore, I'm going to draw its elemental symbol, and it gets 1 dot. Argon has how many valence electrons? Well, we count across, we find argon in the noble gases. So we count across the periodic table in period 3, so the row 3. We count sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon. We've counted 8 things across. That means that argon has 8 valence electrons. So argon symbol. And when we draw our electrons in, we go around in a circle once, adding 1 electron to each of north, south, east, and west, like a compass. Once I've done that, I can start filling them up. I can start pairing. So I need to pair up all of them. So we should see something with 8 electrons around it. I'm just going to add one more example here. Let's do bromine. So bromine is E. Bromine, we need to count the number of valence electrons. Bromine is in period 4. Now, period 4 differs from period 3 in that the transition metals are right there. So what we might want to do is count across potassium, calcium, scandium, titanium, vanadium, chromium, manganese, blah, 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 arsenic, selenium, bromine. That would give us 17. But 17 is way more than an octet. What you need to know is that transition metals, all of the electrons that we would count across from a transition metal actually go in their own orbital, okay? So if you're thinking of something like the first level has 2 electrons, the second level has 8 electrons, so does the third level, and then we get to the next one and you want to add 18. 18 does not work. Okay, so what it'll do is it'll add those first 2. So if we're working from bromine and we're drawing this big diagram, it'll add the electron from potassium and calcium. And then what it does is it adds an inner orbital. So just in between these last 2, it adds 10 electrons from all of the way across our transition metals. 1, 2, 3, 4, 5. Fills that up. That is now full. So once we get across our transition metals, it pops back out to this outer ring that we've already got 2 electrons in. And it says, cool, let's keep going. Gallium's electron, germanium, arsenic, selenium, bromine. So bromine actually only has 7 valence electrons. So when you're counting valence electrons, skip across the transition metals. You don't have to know too much more about this and why they go into their own, or even that they do. When we're counting our valence electrons, just skip across your transition metals. Don't count those. Okay, so what that meant was we counted potassium, calcium, gallium, germanium, arsenic, selenium, bromine. And if I counted out how many elements it took to get there, that was 7. So bromine's diagram, I get to go around once. That's 4, 5, 6, 7. Okay, so when we are drawing the electron dot diagram of an element, we are simply going to draw the valence electrons only. Finish up that chart. Practice problem number 6, we were drawing the elements. Elements are neutral. Now we are going to draw the electron dot diagram for their ions. So let's do fluorine and barium. Fluorine has 7 valence electrons as an atom or an element. The most common charge for fluorine is -1. So what we know is that fluorine would have looked something like this. Now, to get a negative one means that we are gaining an electron. Negative charges come from electrons. Electrons being added. So I'm going to add 1 electron to fluorine, the atom, and it becomes an ion. Now, we don't have to draw that electron as being any different. I could not tell you which electron it was that made fluorine become an ion. However, I do want to note that I didn't make a mistake in just drawing fluorine, that I meant to draw this because fluorine is an ion. So when I draw an ion, I have to include square brackets around it with a charge. Okay, so its charge is -1, and that tells me that there's an extra electron somewhere in this diagram. Barium typically has 2 valence electrons because barium is in group 2. Down in period 6, so row 6, I count 2 electrons. So barium would look something like this. Now, to become an ion, something either wants to gain electrons to get 8, so we gain to 8, or we lose to 8. All right, or to 0, I guess it will look like. So what happens here? Barium's common charge is 2+. 2+ means that we lose 2 electrons. So these electrons left. If they left, technically, barium has some core electrons or inner levels that are full, so it's got its octet. But its outer level that we just drew, so this level, if I take away those 2 electrons, it's empty. So that is barium's ion diagram, an empty shell with a 2+. So when you're drawing an ion, you want to either have 8 electrons or no electrons in that shell, depending on whether it lost or gained. So go ahead and finish those 2 practice problems in your notes.